Hi everyone, and welcome to the 10th and final part of this formal logic video series. In this session I'm going to look at the exam answers to the 2009-10 exam paper, which is available at the following website. If you go to your search engine of choice and type in University of Manchester and past papers, you'll be taken to this page, and then if you just type in Introduction to Logic in the search bar, you don't need to set any of the other parameters for the search. You should get presented with 5 or so papers, and I'm looking just at the 2009-10 paper. And I'm also just going to be looking at the proofs in QL and PL and the translations into QL from that paper. And they're worth 60% of the mark, so that's a 2-1 there if we answer all of those right. I'm not going to go through any of the rules that we've covered on the course so far in this session, so if you still feel unhappy or are unsure about any of the rules that we might need to use in proofs, then please just go back a few sessions and watch the relevant video series episode for that rule, just so that you feel comfortable in using it and you know what's going on, because I'm not going to do much in the way of explaining how each of the rules work. Rather, I'm just going to look at each question and work through it in what I consider to be the most methodical way, as it's been taught to you throughout this series. It's worth noting as well at the start of this that for a lot of these questions there may well be more than one way of answering it. There might be, with the proofs, there's always going to be longer proofs that we could give of any proof, but there might just be completely different ways of going about it. So if you don't have in your mock answers the exact same answer that I've got here, that doesn't necessarily mean you're wrong. It just means that you may have a different answer. So in assessing those kind of concerns, I would just look and make sure that if you've applied the rules correctly in each way, if you can look at each step that you've taken and relate it to your kind of cheat sheet of the rules that shows you how they each work, and if it all lines up and it's all fine, then great. If at any point you get to a part where you think, well, I'm not sure whether this would work, it's not quite how it's written here, then it's probably wrong. The rules only work in the ways that they're stated, so just bear that in mind. But hopefully we'll have all clocked on to the same sort of method to these questions. So let's have a look at the PL proofs first. So 4.1 on the paper is a categorical proof, which we can see we've got our turnstile at the front, we've got no premises, and it's if not P then not Q, then Q then P. So if I'm thinking about this structurally, then I already know roughly what the proof is going to look like, and I can draw that in now. I think that's the first thing that I'll do. So my main scope bar is going to go there, and I know that I'm ending up with that sentence, so I can write that in. If not P, then not Q, then Q, then P. And just looking at this sentence that we've got at the bottom here, its main operators are conditional, so I'm going to try and introduce it with a conditional, and that tells me that the rest of the proof has to look something like this. I need to have a second scope bar that ends with Q, then P, ends with this consequent, and begins with an assumption of not P, then not Q. So that's my step 1. And just to make this more obvious, that is the 2 halves of our conditional at the bottom. Okay, so I just need to get from not P, then not Q, to Q, then P. Again, I've got another conditional statement here, so let's try and introduce it again with a conditional introduction, a horseshoe introduction. So again, that requires me to have assumed that Q and show that P follows from it. So I've not really done any operations yet. I've not, worked out how I meet in the middle, but just noticed that I've already got quite a lot written down. So I think this is definitely the way to go about it. Use up a lot of space drawing out what you think the proof is going to look like. Fill in the gaps, or fill in the space that you've got to start with. Just getting from Q to P is a lot less of a job than just looking at this categorical statement, this categorical sequence, and thinking how on earth am I going to get to that. So again, I stress this every session. I think try and write out, work out the structure and draw all that in. It will really help you to then see what we need to do. I mean, presumably we can now see that, okay, I need to get to P, but I don't have any obvious way of getting that. I can't derive it from Q. It's not got a main operator, so I can't introduce it by its main operator's introduction rule, and it doesn't look like I could reiterate not P then not Q. It's not a part of that either. So let's try getting it by an indirect proof. So again, I'll draw in everything that I know I'm going to need if I'm doing an indirect proof. The first thing is that it's going to end with not P being turned into P, and it's going to start with another subproof. So on line 3 we're going to have a subproof that begins with the assumption that not P. And now I just need to work out, so in fact I'll fill in as well the rules that I'm using here. Conditional introduction, another conditional introduction, and then this is going to be negation elimination and negation introduction. Here we've got an assumption, and a third assumption. Okay, so how do I get from Q to P? Well, I'm going to do an indirect proof, so I've assumed not P, and I need to show that that leads to some kind of contradiction. Hopefully, obviously, now we can see that this first premise, it's not a premise, sorry, this first assumption, if we reiterate that up here, not P, then not Q, then I can derive not Q from it. Seeing as I've just assumed P, I can use that as that's the antecedent of this conditional, so I can get not Q. But I've also assumed Q, so I can just reiterate up Q. Sorry, that one is 3, 4, conditional elimination, and then this one is a reiteration of 2. 2 reiteration. So there we go, that gives me my 2 contradictory statements. 5 and 6 give us 7, which is from 3, 5, 6, negation introduction. 8 comes just from 7, and then we've got our 2 conditionals. So on line 9 we get Q then P from 2 to 8, and we get not P then not Q then Q then P on line 10 from 1 to 9. Okay, so I said at the end, look, now it seems kind of obvious what we need to do once we've assumed not P, but that probably wasn't obvious that we were going to end up doing something like that from the very beginning, or it may not have been obvious that we'd end up with our proof looking exactly like that. And that's why, just by thinking, right, what is this step going to be, and not just thinking what rule might I use to introduce it, but actually drawing out what the proof would look like if you went about it in this way. Because eventually we keep making these very easy steps and thinking, well, it'd look like this, and then this second section would look like this. Eventually we get to a point where it's just obvious how we get from the top to the bottom, and that's what we want. We want to get to a point where it's just really easy to see what we have to do. Okay, so there is 4.1. Let's move on to look at 4.2. So, not A or B, A then not B, and A, therefore A and not A is our sequence that we're going to try and prove. Again, let's draw in everything we can just from that sequence. So line 1 we're going to have A, not A or B, sorry, 2 is going to be A, then not B, 3 is A, those are all premises, and then we're working towards this conclusion. Let's just put a Z here so we know this is our conclusion, and that's A and not A. Now there are two obvious ways of doing this that I can see. They both use similar methods, but they differ significantly in that the way we eventually introduce this sentence is different. So one of the ways, and perhaps maybe the more obvious way, not sure, would just be to introduce this sentence A and not A with a conditional introduction. We've already got A, so that would just mean we'd need to have not A on this line here. And how might we get that? Well, let's try and do it. There's two ways once we've done that, but one way might be, well, let's do it by its main operator again. We'll assume A and show that leads to some kind of contradiction. Well, A entails not B, so that's half of it. But also, if we reiterate up not A or B here, if you remember from a previous video, we said that if we've got a disjunctive statement like A or B, and we've got the negation of one of those sentences, something that would contradict one half of the disjunction, then we can derive the other half. And here we've got A, which contradicts this half of the sentence, not A or B. So with a disjunction elimination in here, disjunction elimination, we would be able to get B from that. And then of course these two contradict, so we could introduce not A. Now that's a perfectly valid way of doing it, but we're doing a disjunction elimination of not A or B, and personal preference of mine is that I just like to have those as the kind of main step of the proof, right? The kind of the step with the widest scope. So I'm going to do it as a disjunction elimination of not A or B. Basically, because these contradict one another, not A or B, A then not B, and A are contradictory. And we can see that just by thinking, well, look, if A entails not B, and we know that either not A or B is the case, well, look, A is the case, so that's the opposite of this side, but A entails the opposite of the other side, right? So they've got to contradict one another. So we should be able to do a disjunction elimination and end up with what we want, the formula that we want. So that's going to require two subproofs. First one is of not A to A and not A, and the second one is kind of indicating that I've already thought about how long these are going to be, but again, all I'm doing here really is just drawing in structure that I know has to be here if I'm doing a disjunction elimination as the final step. So this other subproof has to begin with the other side of this disjunction, B, and it has to end in A and not A. So again, I just want to drive home that without really doing much of the proof at all, I've written a lot. I've got pretty much the whole, from top to bottom, I know what the structure is going to look like. And this is really going to help me in working out what to do next. So I can, and as well, I can just treat these proofs separately now, these two subproofs. So I want to get from not A to A and not A, and I can use these premises. Well, that's really easy. I can just reiterate up line 3 onto line 5, reiterate up A, so that was 3 reiteration, and then that allows me to just do a conjunction introduction on line 6, so that would be 4, 5, conjunction introduction. Okay, so that's that half of the proof done. I've shown that one half of this disjunction leads to A and not A. What about the other side? So on line 7 we've got the assumption that B, and I want to somehow get down to A and not A. Well, that's going to require me to have A, which I already have on line 3, so I'm going to reiterate A there, and I would also need not A in order to do this conjunction introduction. introduction. So that is going to be oh well, we're not sure how we've gotten that yet. Well, how about if we assume A and then we reiterate up A then not B in order to derive not B, and then just reiterate up our assumption of B. So 7, 8, 9, 11. So this little subproof here, I just thought, let's just do an indirect proof. There's no obvious way of getting not A from B. So assume the opposite of what I want. We'll assume A, reiterate up line 2, and then 8 and 9 give me not B through conditional elimination, and then I can reiterate up line 7, and there's my contradiction. 10 and 11 contradict one another, so on line 12 there's my justification. 8, 10 and 11 negation introduction. 13 is just a reiteration of 3, and we've already got the rule written in, so then 14 and the last one's 15. So there we go. As I said, there was that other way, that other potential way of doing it, and there's probably other ways that we could go about it as well. I think all of them are going to involve doing some kind of disjunction elimination. So if you've got a disjunction elimination in there somewhere, then you're probably on the right lines. Just make sure if your answer looks different to this that you've followed all of the rules as closely as you can. Okay, so here we've got another categorical proof, and this one is if P then, add another bracket on here, if P then not P then Q or S. So let's make a start. I've got no premises at all, but I know that I'm working towards having P then not P then Q or S. Okay, so now its main operator is a conditional, so I'm going to try and do a conditional introduction, and of course that just lets me draw in the whole structure of this proof. I know that I need a subproof that ends with not P then Q or S, and that's got to have begun with P. And notice that I can draw this subproof right up to the top because I know I've got no premises. This has to be what came first. So there we go. That's an assumption we started with. So how might we have gotten not P then Q or S? Well, again, its main operator is a disjunction. So let's try with a disjunction introduction. So we would have needed either not P then Q or S, just on their own here. Now I think that a good bet is that we would have come from not P then Q, for the sole reason that we've assumed P. So we don't have any S's at all, and it's just a standalone statement. We won't be able to derive that, whereas even if it's not obvious at the moment how we'd get not P then Q, it's at least obvious that it's going to be easier to get that than it is S, because we've started off with one of the symbols, one of the formulas contained within this more complex formula. So how could we get not P then Q? Well, again, it's conditional, so let's do a conditional introduction, and that's going to require assuming not P and showing that it leads to Q. Okay, now we're in a position where we don't have any main operators here, and it's not obvious that Q follows from these formulas in isolation, so let's try and do an indirect proof to get Q. So if I'm doing an indirect proof, that means I assume not Q, and I show at least some kind of contradiction, and I get not Q, and that lets me do a negation elimination. So what kind of contradiction can I create? Well, again, hopefully obviously we've assumed P, and then we've assumed not P. So we'll just reiterate up those two formulas, P and not P. So that was 1 reiteration and 2 reiteration, and then on line 6 we can write from 3, 4, 5, negation introduction of not Q, so 7 is 6, negation elimination, and then we've got all our conditionals sorted. So line 8 we get not P then Q from 2 to 7. On line 9 we get not P then Q or S from 8, disjunction introduction, and then on line 10 we've got our whole thing coming in, so lines 1 to 9 and a conditional introduction give us P then not P then Q or S. Okay, moving swiftly on. Question 4.4 is not S if and only if T, so that's not S if and only if T, negation of that by conditional, G or S if and only if T, and G, therefore G. So again, we'll just be very methodical with all of these things, just like everything in logic we can be mechanistic about it. We've got a set way of doing everything, which will hopefully lead us to the answer. So let's say Z is for G, premise, and it's not clear how we're going to get G yet. Okay, so this is what we're starting off with. Now, okay, in this proof here, we said, look, if we've got a disjunctive statement, not A or B, and we've got the reversal in terms of truth value of one of those, one half of that disjunction, so here we had A, which contradicts not A, then we can derive the other side. Well, let's have a look here. We've got this disjunction, G or S if and only if T, and we've got the negation of that statement, not S if and only if T. So we should be able to derive G through a disjunction elimination, because we've got something that contradicts the other side of that formula. As I say, I went through a very similar, in fact the exact process that I'm going to go through here in one of the earlier videos. So when we've got a disjunction and we've got something that contradicts one half of that disjunction, it's a bit long actually, we can do a disjunction elimination, so we need 2 scope bars. The first one, we're trying to derive G, so we just assume G, and that shows that G follows from the assumption that G, so we don't need to worry about doing any more there. And then on line 4 we'll assume S, bracket there, S if and only if T, and we need to show that that leads to G. Well, how are we going to do that? Well, look, we've now got the assumption that S if and only if T, and a statement on our main scope bar that contradicts it, not S if and only if T. So we can just do an indirect proof to get to G. Assume not G, assume the opposite of what we want, and then reiterate up our contradictory premises. So S if and only if T, and not S if and only if T. So that's from 4 and 1. That, of course, gives us not G, so 5, 6, 7, negation introduction, and so then on line 9 we can write G from a negation elimination, and on line 10 we just get G because we've shown that G leads to G and S if and only if T leads to G. So that's disjunction elimination of, so that's from 2, 3 to 3 and 4 to 9, disjunction elimination. Okay, so quite a simple proof really. Once we put the structure in, they're all quite easy. Another disjunction elimination, just as we had up here. In fact, marks off for me if I hadn't have spotted this. Not A and A, so 12, 13, conjunction introduction, and 15 is from 4 to 6, and 7 to 14. So there we go. Even I forget sometimes, but make sure that you go through your paper at the end of the exam and ensure that all of the rules are written in correctly, so that you've got all of the numbers of lines written in, because you will lose marks for that, and it's completely unnecessary, especially when you've done the proof correctly. You know, in a way it'll just mean that it'll take us longer to read it to work out what you've done, but you have to lose marks for not citing the justification, because it won't always be clear that you do understand how the rule works if you haven't cited the correct lines. So make sure that you do go through at the end of your paper. You'll have 3 hours for this exam, so lots of time to write out the exam and then go back and check each and every line, make sure that you've justified it in the right way. 3, 5 and 6, yeah. This one, okay, I've already looked at my mistake there, 2 marks off for me. And yet this one, 2 to 17. Okay, look, I haven't cited a rule here, so that's a conjunction introduction. So I'm trying to speed through this, and that's causing me to make mistakes in my recording of the proof. So make sure that you don't make similar mistakes in your exam. Okay, I think we're up to speed now. So let's move on to the next question in the paper, which is the translations into QL. Again, I'm not going to dwell too long on each one of these questions, and I'm going to assume that we know roughly how to do these translations. So, John is someone who likes everyone. Well, just looking at this, I've got John, so that's a subject, J, is someone. So I mean, here we've got a sum statement, right? That's an existential statement. Everyone designates to me that there's going to be a universal quantifier, and who likes, right? So likes is, I think, a relational predicate. Right? So we might have likes 1, 2. Now with this question as well, we've got the use of the word someone, right? Because we say someone, everyone, we're talking about persons. Right, so we'd have, you know, a predicate, one, such and such is a person. So there is a way of writing this in which we use that predicate, but remember we can restrict the domain of the sentences, and because we're only talking about persons in this example, it's safe to just say we'll restrict the domain to persons. So x is a person just means that any variable I use now is going to refer to a person. So I've restricted the domain of my variables, of the things I'm quantifying over. Okay, so now I just need to write out this sentence. John is someone who likes everyone. Okay, well, really that's just a case then of saying John likes everyone. So how might I say that? Well, I've got this existential statement, so presumably that's going to come first. Every x is such that, so I just need to work out the such that. Well, if I've got my predicate L, which is going to be 1 likes 2, in fact I'll move that up there. Jot this out of the way. And just to make clear how the keys are in. I really like writing the keys in this way, where we have dot 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 1 dot 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 2 to just designate that we've got 2 spaces for subject letters in this predicate, right? It's not going to be complete unless we've got those 2, and then we show how they line up in the translation. So such and such 1 like such and such 2. Okay, so what is true of everything? Well, that John likes them. So every x is such that J likes x, and because we've restricted our domain to persons, we don't need any other predicates in here. If we weren't restricting the domain, then we'd need this person predicate. 1 is a person. Terrible writing. 1 is a person, and I think we would have ended up with something like this. Every x is such that in fact, maybe we would have started off with John is a person, and for every x, if x is a person, then John likes x. So there's a slightly longer version, but because we restricted our domain in the version that we gave, because we had this bit, we didn't need to have this second bit. Yeah, we didn't need the longer version of that question. But in the exam, either one of those would be fine. Right, so long as we state our key correctly, and if we are doing domain restriction, it's not just left implicit, right? We do need to write this restriction, x is a person. And remember again that just x is a person doesn't mean that every variable x will stand for a person, so that if we had a variable y in there somewhere, that would be something else. It just means that every variable that we could use, right? If I had used, I could have written x is a person, and then had every y is such that John likes, John likes y. Right, that would have been perfectly fine. The domain still would have been restricted for these variables. This is not a key statement like this. It's a statement about the set of things that the variables we're going to be using can refer to. So just bear that in mind when you're doing this. Okay, so question 2. Mary is loved by someone other than herself. So again, let's go through this. Well, we've got Mary, so that can be small case m, that's a constant. Is loved by, so there's a predicate. 1 is loved by 2. We've got a someone, so again, exists an x, and the one bit designates to me that this is a person predicate. Let's just make all that clear. Other than herself. Okay, so the fact that we're going to be talking about distinguishing Mary from any of the variables we're talking about means that I'm going to have some kind of identity statement in there. Now again, we're only talking about persons here, so I think we should be restricting our domain to persons. That's going to make things a lot easier for us. Now for the rest of our key. In fact, look, I missed another thing from my key here, which was J is John. So make sure you're not missing things like that. Again, if you miss things out of your key, you're going to lose marks unnecessarily. So make sure you go back at the end of the paper, check through every question, as laborious as that is, and ensure that all your keys are in order, all of your justifications for proofs are in order, because they're just silly marks to throw away. So in this case, we're going to have M is Mary, and then we've got a predicate for is loved by. So 1, 2 means one is loved by 2, and we've got so we said we had this person predicate, but I don't think we need it because we've said that we're restricting the domain to persons. So we should just be able to start going about writing this now. So if Mary is loved by someone other than herself, that means that there exists someone who loves Mary, and that thing isn't Mary, right? So there exists an x. Yes, I did put brackets around my quantifiers. There exists an x such that Mary is loved by x. That's the first half of our statement. And the second thing we need to say is that that thing, that x, is not identical to Mary. Okay? So there exists an x, that Mary is loved by that x, and x is not identical to Mary. And remember, because we've restricted the domain to persons, that means that this thing has to be a person. So there is someone who loves Mary, and it's not Mary. The last thing to do is just to make sure that the scope of our sentence is right. So at the moment, remember that quantifiers have scope over the next well-formed formula. So here, the EX, the existential quantifier that's binding this X, only has scope over LMX. So we need another set of brackets just here so that the X in this identity statement can be bound to this quantifier too. Okay, so that's another thing to look out for. easy to make mistakes on with the scope of quantifiers. Just make sure that if you're using a variable anywhere in the sentence, that it comes under a larger bracket. It comes under the scope of one of the relevant quantifier. That's really important to look out for. Okay, on to 5.3. So more than two things exist. So again, let's think about this. We've got so more than. Well, let's just we'll just do a little more than symbol here for the time being, but we'll think about how we'll do that in a second. Okay, we're talking about the existence of things, right? Two things, more than two things existing. So it's going to be our existential quantifier. We've got no other predicates in there, but because we're going to be wanting to say that more than two things exist, we're going to need some identity statements. So one way of saying that more than two things exist is to say that at least three things exist and none of those things are identical to one another. Okay? If at least three things exist and none of them are identical, then there must be more than two things. So we'll start off with our existential statement. So there exists an X, exists a Y, and there exists a Z. And what is it that's true of these things? Well, it's not the case that X equals Y. X equals Y, or Y equals Z, or X equals Z. Okay? So there we go, simple as that. We don't need to do any domain restriction here because we're talking about things. And in their most abstracted state, the variables here just refer to things of a particular kind. Okay, so a quick question there. Just remember this formulation, right? That if we're saying that more than two things exist, we're going to need to just say that there are at least three things, and none of those things are identical. So X doesn't equal Y, Y doesn't equal Z, and X doesn't equal Z. Okay, question 5.4, last one of this section. No one knows someone who knows everything. So this one is a little bit more complicated than the others, but if we work at it methodically, it shouldn't be too bad. So, okay, look, no one. So, first of all, that tells me that's going to be a not EX, right? When we've got no one or nothing, the most obvious way of translating that is there's no X such that. Okay, we've got one here, and we've got someone, so I think that tells us we're going to need a person predicate. Sorry, it's not two place though, just a one place person predicate. Okay, knows, that is going to be relational, right? X knows Y, and everything. Okay, so we're going to need our universal quantifier. Now we might be tempted to try and restrict the domain here again to persons, because we've got no one knows someone who knows everything, but the problem is because we're talking about everything here as well, right? We're saying knows is relational, so we're saying somebody knows everything as a relation. It's the relation K, right? They hold this relational property to everything, and everything includes non-persons. So we can't restrict our domain here. We're going to need to include our person predicate. So let's write all this out. We're going to have P is a person, and K is 1 knows 2. Okay, so this is a slightly more complicated one to translate, but let's try and break it down into parts. We want to say that there's nobody who has a particular complex property, the property of knowing someone who knows everything. But that in itself is split up into two parts, right? We need to be able to say that there is someone who knows everything. So someone who knows everything is going to be something like exists an X such that X is a person, and for all y, x knows y. We don't need that second bracket. We do need brackets around these quantifiers. Okay, so there's someone knows everything, and what we want to say is that there's nobody who knows someone who knows everything. Right, so say there's no z such that z is a person and there is someone who knows everything and z knows that person. Yeah. And there we go. Simple as that. And notice that we have to make sure our brackets are all in order here. We've got quite a lot of brackets. So pick it apart carefully. Make sure that everything comes under the right scope. So we want to say there's no z such that all the z's have to be under this scope. So this bracket starts here and ends here. So that encloses this. Then we've got the second bracket and the ex having scope over just these two parts. So that's wrong, right? We need to have the x having scope over the x here. And just notice that this x, sorry, just the x from here has to bind both of these, sorry, all three of these. So that means that this bracket here has scope over everything in this bracket. There. So then we need another bracket on the end. So now we should have 1, 2, 3, 1, 2, 3. Yeah, so we're right. Okay, so this here is the outer bracket. So this is for the z, has scope over everything. And then x is the yellow bracket, so that has scope there. And then the y just has scope over this sentence here. Yeah, it just has scope over that because there's no extended bracket. Okay, so just notice that we built it up in that way. We thought, how would we say that someone knows everything? Because what we need to say is that there's no person such that they know someone who knows everything. So we built it up from kind of that smaller statement there. There are other ways that we could have written this. If nobody knows someone who knows everything, then it means that of all people, well, this is true of all people, that if they know someone, then that person doesn't know everything, or if somebody knows everything, then they don't know that person. So let's have an attempt at that. Just say that every x is such that if x is a person, then for all y, if y is a person and knows everything, so that's our for all z knows yz, then x does not know y. And we're going to need another pair of brackets there. Okay, so we've got every x is such that if they're a person, then for all y, if y is a person and y knows everything, then x does not know y. And again, I think that's just a different way of approaching this question. Right, let's move on to the quantifier proofs. So 6.1, we've got all y is such that if fy then gy, there exists a y such that fy and gy, therefore there exists a y such that gy and fy. So we're trying to get to the kind of the fy and gy swapped around here within the bracket. So let's draw out our scope bar. two premises that we've got. GY, and we're trying to get down to Z, which is exists a Y such that GY and FY. Okay, so what might we do here? Well, we could do a universal elimination on this. I mean, this, if we're thinking about how we'd introduce this, its main operator is an existential statement. So maybe we could think, like, if I could get let's just say GA and FA, then I could do an existential introduction down to this. So I would need FA and GA on their own, but there's no obvious way of getting those from the premises, so it looks like that isn't going to be the right way of going about this question. So the other thing that we could try and do is get it by elimination of one of these. Well, if we eliminate the universal quantifier, we're just going to get, say, FA then GA, and we'd need FA then to plug in order to get the other side, and we don't have that. So the only other option, really, if we're doing an elimination, is to eliminate this existential quantifier. So if we're set on that, what that tells me is I need a subproof. So it's a parameter subproof, right? We've got this parameter introduced, U, and that gets fed into here, so I'm going to end up with FU and GU as an assumption on line 3. And that has to lead down to this exact formula. Remember, the way that existential eliminations work is that we have a subproof that begins in this modified version of the existential statement where we've eliminated the existential and swapped out the variables it bound for the parameter of the bar we're working on, and then we end up with the exact formula that we want to derive, and we can just move it down and to the left, so long as it doesn't include any of those parameters. Okay, so we need to get from FU and GU to there exists a Y such that GY and FY. Remember, we said before that if we had a statement like GA and FA, then we could just introduce this by existential introduction. Well, we don't have any A's, but we are on a U parameter bar, so why not GU and FU? And where might we get those from? Well, we know that we can do conjunction eliminations, so we could get FU from 3, conjunction elimination, and on line 5 we could get GU from 3, conjunction elimination. So on line 6 we can just recombine those, 4 and 5, conjunction introduction, and so that gives us, we can then do our existential introduction on 6, existential introduction, and so we end on line 8 with 2, 3 to 7 existential elimination. So this was kind of a trick question because we didn't really use this premise at all. We didn't need that. We could have kind of started our proof with line 2. We didn't need that line at all. It didn't play any part. But that's okay. It doesn't mean you don't need to use every premise in a proof when you're doing it, just so long as you show that those premises entail the conclusion. Okay, 6.2. So this time it's, let's run our scope bar. We want to get from there exists an x and there exists a y such that rxy to there exists a y such that there exists an x such that rxy. So we want to swap around, that's all we're doing here, we're swapping around these two. So start off with our premise xey rxy, and our conclusion is ex rxy. Okay, so how might we get down to this? Well, look, we've only really got one thing to work with here. We're not going to, we could do this from, say, if we worked back with existential introductions, we could get rid of the y first. We'd have ex, say we had rxa, and then we get rid of that, so we'd have rba. But where is that going to have come from? We're not going to get it from this, so doing it by the introduction rule, the existential introduction, isn't going to work. So what about an elimination? Well, the main operator of this is an existential, so that's going to involve going on to a u parameter bar, ey r uy. That's going to be our assumption on there. And that would have to end up with ey has to end up with the exact formula that we want. ey ex r xy. Okay, again, how could we get this? Well, it looks like we'll be doing another elimination. That's the only rule that we have at our disposal here. So we'll go on to a second parameter bar, this time using the parameter v, swap out the y's and have r uv, and we need to get down again, exactly the same thing, we need to get down to ey ex r xy. Okay, so how do we get to that? Well, now we have got this formula with two, here it's parameters. We said if we had have had RBA, then we could have gotten to this. Here we can just do our existential eliminations on RUV. So the middle step is going to be on line 4, and work backwards as well. Think about what would have come before this. We'd need to have put the EY on last. Right, so the steps we do this in is going to determine what we end up with. If we needed to do the EY last, that means that what we'll have had is this part of the sentence here, EX RXY. So let's do that, EX RXY, and that's going to be from 3, existential introduction, and then on line 5 we'll do another existential introduction from line 4. So that lets us introduce on line 6 EYEX RXY, and that's going to have been from line 2 and then lines 3 to 5, existential elimination, existential introduction, and then line 7 again, same thing from line 1, and lines 2 to 6, existential elimination. Okay. So again, just weigh up your options. Write out as much as you possibly can, and then think, how could I get this? Could I get it by its main operator introduction rule? Well, in this case, it looked like obviously not, because we're not going to be able to end up, if we keep going back, taking off existential quantifiers, we're going to end up with a formula that we can't possibly derive from what we've got at the top. So how about an elimination? Give that a go, and then if all else fails, try doing an indirect proof. Okay, question 6.3 is every x is such that if fx, if and only if gx, not ey, fy, therefore not ga. Now, again, we might think it's just not obvious how we do this to start with. Especially if we might think, well, look, maybe if everything is such that it's f if and only if it's g, and something's not f, then maybe what we'd think that entails is, I mean, what it seems to obviously entail is nothing is g. Something isn't g. Right? So some x, well, there's, maybe we'd think it sort of entails something like that, just based on the way that we think these if and only if statements work. Right? If we've got a if and only if b, and we know that not a, then it tends to be that ends us up with, we can derive not b. Yeah. The problem is that, thinking of it in that way, is that this biconditional is contained within the scope of this quantifier, so we can't get at this, and this isn't right. EYFY isn't one of the formulas in the biconditional, so it's not like that case where we had a if and only if b and not a, and then we derive not b. What we've got is a different formula here. This is different to the formulas connected by the biconditional. So let's just, even if we don't know exactly where we're going to end up, let's just start writing out as much as we possibly can and see where that takes us. So on line 1 we've got ax fx if and only if gx, and on line 2 we can write not ey fy, and we're working towards not ga. Okay, so what could we possibly do here? Could we introduce this by a negation introduction? Let's give it a go. Sometimes we might not even know how to go about this, but we can just give it a try, right? So doing it by negation introduction would mean assuming GA and then showing that that's somehow contradictory. So if we assume GA, what could we do here? Assumption, premise. Well, look, if we assume GA, what could we do with this, right? We've got all x fx if and only if gx, and we know about our universal elimination rules, so potentially something we can do on this scope bar is to reiterate up line 1 and then eliminate the universal quantifier to get fa if and only if ga. So once we've done that, we can now make use of this biconditional, right? And we can derive on line 6 fa. Okay, how does that help us? Well, we know that this statement says nothing has property f, and we've just said A has property f. A having property G entails that A has property f, but nothing has property f. So if we reiterate up not ey fy, then we can do a existential introduction on fa to get there exists a y such that fy. And there's our two contradictory statements to get us to our not GA on line 9. Okay, so that was for universal elimination. That was 3, 5 biconditional elimination, and then 2 reiteration, and 6 existential introduction. And then, so the last one is 3, 7, 8 negation introduction. Okay, so again, it's just a case of if we start putting things down on paper, or the blackboard in this case, things will start to pop out at us, things that are ways of doing it. This did require a little more thinking perhaps than the ones in PL, because we've got to think, well, if I've got GA here, I can do a universal elimination to get at the fx if and only if gx. Right, so it's sometimes not quite as obvious. And then if I have fa, I could turn that into a statement that would contradict not ey fy. Sometimes the thing to do, especially when we're doing negation introductions or indirect proofs, is just to have a look at the formulas we have. So there we had ax fx if and only if gx and not ey fy. It's just to have a look at these and then maybe write in the margin of, you know, whatever you're doing, the statements that would contradict those. So if you're doing an indirect proof, this is right, this would contradict that, and ey fy would contradict that. And really, looking for contradictions is as simple as either popping a negation on the front of a formula or taking a negation off the front of the formula. Okay, so if we were thinking about this, if we had these in our margin, we were thinking, okay, how could I possibly derive one of those two things? I'm on the lookout for them. Well, then maybe it would have been a bit more obvious that, okay, if we assume GA, that might allow us to get, if everything that has property, if something has property f, sorry, if and only if it has property G, then GA implies FA, and of course I can create EY FY from that, and that's one of the formulas that I want, that's one of my contradictions. Yeah. Okay, so just something to think about. So just write this for future reference. So look for the formula contradict one of your premises or existing formulas. Above. Okay, and that's for an if you're doing an indirect proof. Okay, let's look at the final question then on the paper. So 6.4 is another categorical one. I actually think, so some people kind of get a bit worried about categorical proofs. It sort of seems daunting that we don't have any premises, but I think they're easier, right? We don't have to worry about how we can do something from the premise. We just have to think about why this is self-evident. Okay, so we're trying to get down to not ex, not x equals x. So there's nothing such that it's non-identical with itself. Right, that's what we're saying here. Nothing is non-identical with itself, which again is self-evident. How am I going to get down to that? Well, its main operator is a tilde, so I'm going to do a negation introduction. So I'll start off by assuming something that is obviously contradictory. Something is non-identical with itself, and then I'll show that that leads to some kind of contradiction. Okay, well, as I said before, if I'm looking for a contradiction, what I should do is look at the things I already have, what I want to be creating. The only thing that's going to be useful here, the only thing that would contradict this is, so let's just kind of have it up here, not ex, not x equals x. Like that would contradict that. Okay, so if I can derive this on this scope bar, then we're done, right? We've shown that. Now you might worry that, look, that's the very formula that you said we were aiming for. That's why we're doing all this, to derive that. But now we've kind of got something that we didn't have before, which is this assumption. This could be useful in creating this on this line, and then that will help us to get there. So, okay, how might we introduce this statement? Well, look, one might be to say, okay, well, if I've got to introduce that, let's write it at the bottom. Not ex, not x equals x. If I've got to introduce that, one way might be to do a negation introduction. Right, so I'll assume ex, not x equals x, and show that that leads to a contradiction. What would contradict it? Oh, this statement would contradict it. So I'll try and work. Okay, you get the point, right? That way is not going to work, because that's the method that we're trying. Right, we're just repeating what we did before. We're just getting kind of an infinite proof, an infinite regressive proof. Right, we do want to get towards having this here. Not ex, not x equals x, but we can't do it by indirect proof this time. But as I say, we now have this extra premise, so can we eliminate it from this? Let's give that a go. So if we're doing an existential elimination, that means that we end up with the very thing we're trying to derive. So we end up with not ex, not x equals x, and we start off with an assumption. So here we're going to be on a u parameter bar, so we'll start off with not u equals u. Okay? So, how do I get from the assumption that not u equals u down to not ex, not x equals x? Okay, again, we could try doing it with its main operator, right, a negation introduction. And now you're going to say, well, Chris, you just said that was silly because that's what we were doing. But now we're on a different scope bar. We've got something else added. So it is going to be worth trying that, because we've now got extra information. Before, we were just embedding the exact same operation on that operation, right? We're going to try and do a negation introduction of not ex not x equals x by doing a negation introduction of not ex, right? That's not going to work. But here, if we try and do a negation introduction, we're doing it on the basis that we've assumed that u doesn't equal u. And again, that's obviously contradictory, right? That something is non-identical with itself. So let's make our assumption. There exists an x such that x does not equal x, and try to show that that is contradictory. So let's just write. So these are all assumptions. It's categorical. Assumption, assumption, assumption. So again, let's just think now. We've got another premise here. We know that if we can create not ex not x equals x, that would contradict this. But again, one way we could do that is by doing a negation introduction. That's not going to work because we're trying to do that here. That's the step that we're on. The other thing we could do is try and eliminate it from this existential quantifier, but that's what we were doing here. Okay, so there's where we get our kind of recursion, where we get our repetition of the method. So let's look for contradictory premises again, right? The first time we looked for this would contradict that, but now we've got not u equals u, and what would contradict that is just u equals u. But if we remember our identity introduction rule, we can write u equals u anytime we want. We just have to put identity introduction at the side. So we can get this for free, really, because we can just write at any time that u equals u, or any constant parameter equals itself. So then on line 5 we can reiterate up x, not u equals u. That's a reiteration from 2. And that, of course, gives us from 3, 4, 5 our negation introduction to not ex, not x equals x. We were doing a existential elimination, remember, so it's an existential elimination of 1 and the subproof 2 to 6. Existential elimination. Let me see what that says. So that gives us not ex, not x equals x, and then that on line 7 contradicts line 1. So on line 8 we can write there's no x such that x is non-identical with x. So that's going to be 1, 1, 7. Remember that when we're doing negation introductions we cite the assumption and then the two contradictory premises. So we sometimes double that up if the assumption is the same as one of the contradictory premises. Negation introduction. Okay, and there we go. So hopefully you can see from that one that is a little bit tougher because we had to assume the same thing, twice, and it looked like it was sort of worried that maybe we're just going round in circles. But just be methodical with it. Think of the premises I have, of the lines I have here. What would contradict them? Can I get them from anywhere? And obviously avoid kind of just those kind of, we saw those obvious approaches that were never going to work, right? So one of the obvious, an obvious way it's not going to work, we're not going to be able to get not ex, not x equals x by assuming ex, not x equals x, triple bar, not x equals x, and trying to derive not ex, not x equals x. We can't do that by trying to do another negation introduction, right? Because the only way looks like we can do it is on this next line to have the same thing, not ex not equals x. How would we get that? Maybe we could do it by negation introduction, okay, and so on and so on. We just end up with a proof that went on forever. So we want to avoid this kind of repetition, but here what we did was we did an existential elimination and then we reassumed the premise, right? Because we then had more information. We had another formula that we could make use of. So try and go through it in that way. Always try for, if you completely stuck for what to do when it comes to a proof, Here's the Chris's 5-point plan again. I said in last week. What are you trying to derive? Step 2. What is its main operator? Determine that. Okay, then we get onto our 3. These are the work steps, 3, 4 and 5. Okay, so first thing to try is to introduce it via its main operator rule. The next thing to do is try to eliminate from a previous formula, and then finally do an indirect proof. And if you're doing an indirect proof, the thing to think is, what would contradict what I already have? Okay, so if you think of that and if you write in the things that you think are going to contradict what you already have, it should at least, always be writing in structure, writing out as much as you possibly can of the proof, and things will become more evident. Okay, so that's the end of this video series. I hope it's been helpful and that you've all enjoyed it, and best of luck for your exams.